All right, so today we're starting Unit 16, which is the properties of acids and bases. For the most part, this is informational, and I'm going to leave you to read great bits of this. I'll just go over the stuff that I think we need to talk about. First and foremost, I would like to define a few terms. A proton is a hydrogen atom that has lost an electron. A hydrogen atom that has lost an electron. You will remember in junior high, you said an acid was anything that started with an H. You're refining a little bit and saying, for the most part, an acid has a proton in it. All of your acid-base work happens in solution. So what's going to happen is this charged proton is going to be very attracted to the negatively polar end of water, and they're going to form this, the hydronium ion. You can talk about a hydrogen ion, a proton, or the hydronium ion interchangeably. They're all a distinctive feature of an acid. The properties of acids, I will leave you to read. The common acids and their everyday usage, I will leave you to read. And then I would like to come down to a little bit of terminology. A binary acid means that it is that proton bonded to a nonmetal. Binary means two. The two that they are referring to are the types of elements. There are two different types of elements. One's going to be a hydrogen. I would suspect that on the AP test, given their predilection for particle diagrams, that you should be aware that this looks like a particle diagram for an acid. A ternary acid, ter is the prefix for 3, is a proton that's bonded to a polyatomic ion. It's synonymous for an oxyacid. That's because all of the polyatomic ions that serve as anions contain an oxygen. So it's a polyatomic ion and an oxygen. Here we have some things you should be familiar with. Here we have the sulfate ion, which has a -2 charge. When it forms an acid, it bonds to 2 protons to form the acid H2SO4. Here's a particle diagram of it. It would be called sulfuric acid. Nitric acid is the nitrate polyatomic ion with the -1 charge bonded to the +1 proton to form nitric acids. As a rule of thumb, with oxyacids, the strength of an oxyacid, and we will talk about what strength means in a moment, the strength of an acid increases as the number of oxygens increase. So here would be an example. This is perchloric acid. This is hypochlorous acid, chlorous acid, chloric acid. As the number of oxygens increase, so does the strength. It's a nice multiple choice question. All right, another group of acids that I will just mention because they're tested heavily too is a carboxyl acid. In organic chemistry, there are things called functional groups. You don't know anything about organic chemistry, so let's just say that a functional group kind of acts like a polyatomic ion does. It's a group of atoms that move around as a unit. The carboxyl group is this unit, COOH. It forms acids that have this functional group attached to it. An example of that would be citric acid and malic acid. My picture overrode this word. Here is a base and the properties of a base. I will leave the common bases and their usage for you to read. We will be talking more, and the book talks more about an indicator. An indicator is a chemical that changes color when the acidity or basicity of a solution changes. The two that you positively have to know are litmus paper. And litmus paper is red in acid, blue in base. How do you remember that? I remember it this way. Basic blue with a bees. Phenolphthalein, I bet you already know. In acid, phenolphthalein is colorless, and when it is in a basic solution, it is that beautiful pink color. Beautiful pink color. All right, there are 3 acid-base models that are used in chemistry. One of them has been taken out of the scope and sequence for AP Chemistry, so I'm not even going to talk about it. Please know when you get to college, they will. So we're just going to concern ourselves with these 2. The first is the Arrhenius acid-base model, and it is the most simplistic, and it says an acid is anything that furnishes a hydrogen ion, an H+, in solution. And a base is anything that produces a hydroxide, OH- in water. So this is what an Arrhenius acid would look like. Hydrochloric acid in an aqueous solution breaks down completely into the hydrogen ion and the chlorine ion. That follows the definition of Arrhenius acid. The problem with the model is this. It leaves out a bunch of acidic things and basic things that we know form a basic and acidic solution. The one that I can think of is carbon dioxide in water forms an acidic solution. You know that if you drink Coca-Cola. Okay. Ammonia is a basic solution, but it doesn't have an OH to furnish to water, so it does not work in the Arrhenius model. And all of these must be in aqueous solution, which is really no big deal to us because everything we talk about in this unit will be in an aqueous solution. But that made people look around for another way to define an acid and a base. And pretty much at the same time, a man named Bronsted and a man named Lowry came up with this terminology. An acid is a hydrogen ion donor. A base is a hydrogen ion acceptor. And really, in order for it to be a base, it has to have a lone bonding pair of electrons willing to accept the hydrogen ion. The big thing to note here is these must occur in pairs. There will not be a Bronsted-Lowry acid without a Bronsted-Lowry base being around. For the acid to donate the proton, something must be willing to accept it. All right, the general reaction for a Bronsted-Lowry acid and base is like this. The acid and the base react, where the acid has to donate or give up the hydrogen ion, and the base must accept it. Okay, so what we have after this is done is this. After the hydrogen, the HA has donated the proton, what's left of it is the conjugate base. The base, after it has accepted the hydrogen ion, becomes the conjugate acid. So a conjugate base is everything that's left over from the acid once it's donated its proton. A conjugate is always a product. The conjugate acid is the molecule formed when a base accepts a proton. Conjugates are always products. The conjugate acid-base pair are related to each other because one donates and one accepts. Are we good there? Here's what the pairs look like. Here's the acid and its conjugate base. Here's the base and its conjugate acid. It will be up to you to be able to look at a system and determine which one's the conjugate, which one's the acid, which one's the base, and to find the conjugates on the other side. So if we look at this, we have to decide which one is going to accept and which one is going to donate. If you have the complete reaction, it's real easy to tell, isn't it? Just look and see what happened on the other side. I see NH3 here is different. The difference is it has an extra proton. By definition, then, this must be the base. Water, on the other side, has been stripped of a proton. Therefore, by definition, this must be the acid. Yes?
Why is water an acid?
Water has, let's look at water's Lewis dot structure. And see why it can act as an acid or a base. It can donate a proton, making it an acid. It can receive a proton because of these bonding pair to be a base. That ability to be either an acid or a base is called amphoteric. It is an amphoteric substance. Please look down in your notes and find the term amphoteric. Do you see it? Here is water acting as a base. HCl is donating its proton to water. The conjugate would be Cl and the hydronium ion. Here's the other way. Ammonium is acting as this base and water is donating a proton, leaving NH4 and OH. Here is another amphoteric compound. It has a lone pair and it has a hydrogen ion. Something that can, an acid that can donate a proton is called labile. Labile means that an acid can give off a proton. Acetic acid has one labile proton and 3 non-labile protons. Do you see the difference? It can lose this one, but not that one. Why? This is the polyatomic ion. All right, we are back up here. To look at these a little more closely, let's look at a representation of the compounds themselves in the above reaction. We have NH3 with its lone pair and water with this. On the other side, we see that NH3 has taken a proton while water has lost a proton. HCl has no option but to act as an acid. Why is that? Why can't it be a base?
doesn't have a lone pair with it.
Doesn't have a lone pair, it cannot accept a proton. You can tell from its structure that it does not have a lone pair. Water is acting as the base, it can accept the proton. And these would be the conjugates for that reaction. Good? Moving on. Okay, I would like to make a huge difference in your vocabulary and warn you the difference between concentrated and dilute as opposed to strong and weak. A solution that is concentrated has a lot of solute in it. A solution that is strong completely ionizes. What is a synonym for ionizes? Dissociates. And what does that mean? It breaks apart. So a strong acid completely breaks apart into solution. Pictorially, you can look at it this way. Hydrochloric acid is a strong acid. In solution, 1 molar hydrochloric acid will yield 1 molar proton and 1 molar chlorine ions. Totally breaks apart. This reaction is complete. All of this goes to that. And when you look at it, here it is, ionized completely. There are no HCl molecules in this beaker. It is a strong electrolyte, which means it conducts electricity. There are 6 strong acids. You just have to memorize them. 6 strong acids. In Chem 1, there's, this is the best mnemonic I can come up with, and it's pretty weak. No, so, bur, class, clowns, in Hawaii. No sober class clowns in Hawaii. Personally, I just memorized the 6 strong acids. But it did get me thinking about Hawaii, which is nice. Okay, if it is not a strong acid, it's a weak acid. There's lots and lots and lots of acids out there, just 6 of them are strong. Here's the problem. No one is going to remind you that you're dealing with a strong acid. The calculations that we will be doing with a strong acid are really easy. Really, really easy. Because it completely dissociates. So if somebody asks you, what's the concentration of hydrogen ions, which segues nicely into what's the pH of a hydrochloric acid solution that's 2 molar, you can do that because you know a hydrochloric acid solution that's 2 molar is 2 molar in hydrogen ions. If you're dealing with a weak acid, it's an equilibrium situation and you need to use Rice table. So make sure you memorize your 6 strong acids. Okay. What does diprotic mean?
It's
2
hydrogen ions.
2 protons, 2 hydrogen ions. 2 hydrogen ions. Okay. Now, a weak acid is a weak electrolyte, which means it doesn't turn the light bulb on really strongly in electrode. You remember that in Chem 1? All over the place. Okay.
How do electrolytes, is going off topic, but like Gatorade and stuff?
Actually, if, and maybe I'll do that later, if I took a solution of Gatorade and put a conductometer in it, it does not conduct. It says it contains electrolytes, but it contains so few electrolytes that it does not allow the charge to move through it. What?
Does that actually matter?
Yes, that's how electricity flows. Charge happens. So, back to this. A weak acid or Gatorade, which is actually not even acidic. I think it's pH balanced. I don't know. I try to avoid it. It's candy. Ionizes in a equilibrium situation. This weak acid, how do I know it's weak? Because it's not one of the 6 strong. Dissociates incompletely into the hydrogen ion and the fluorine ion, but at the same time, these two get together and make that. What would this equilibrium situation look like in a beaker? It would look like this. If you were to dink yourself down and see that these molecules were wearing name tags, you will see the majority of them are the compound, and very few of them are the ion. Okay? So the pH would be calculated differently. We'll be doing that a lot. Here are some weak acids. There are lots and lots and lots of weak acids. Here are just some that kids get confused about. This is the one that kids mistake for strong all the time. It's not. Although that is the acid that etches glass. Okay. Now, let's talk about ionic attraction and acid strength. A strong acid has very little attraction between the cation and the anion. More attraction for the proton and some water. A weak acid really likes its anion. So it does not ionize as much.
So weak acids act ionic, basically, like ionic compound.
No, they just like hold on to their.
Exactly. This would be the attractive forces between the H and All right. Now, fortunately for us, strong acid, strong base totally follows the same thing as a strong acid. A strong base is a strong electrolyte. Almost all of a strong base will ionize. The stronger the base, more willing it is to accept a hydrogen ion. That's how you can determine in a Bronsted-Lowry situation who is going to act as the acid and who is going to act as the base. If you are unsure and it's not intuitively obvious, you're going to have to look at a base strength chart that will be included in the question in order for you to answer the question. The stronger the base is, the more likely it is to accept a hydrogen ion. Okay. Now, how do you know if it's strong or weak? For AP purposes, a strong base is any base that contains the cation from a group 1 metal. Everything else is sweet. So there are just a few. A weak base is a weak electrolyte, and only a small percentage of the base molecules form OH ions. In order to find the pH of a weak base, we're going to have to do a Rice table as well. Here are some weak bases. What I need you to get from this is nothing more than familiarity. On the AP exam and in my questions, they will give you the name of a compound, and they don't tell you methylamine, a weak base. They just give you methylamine, and you're thinking, well, it's got some hydrogens in there. Is it an acid? Is it a base? You just need to be aware of it. Which brings me to the topic of amines. Amines are another one of those organic functional groups. It's an NH2, and it's a clue to you that it is a base situation. NH2 forms a base. It's a weak base. And here it is in a number of the weak bases. So all I want you to do is remember the NH2 part, and it gives you a clue as to whether you're dealing with an acid or a base. And that's it for me today. Let me turn this off and then we'll chat some more.